Hi, this is Somaiah working as Assistant Professor in the Department of Mechanical Engineering at Institute of Aeronautical Engineering. Today, I am going to discuss about boundary layer theory as part of Module 3. Previously, we have seen the fluid kinematics, fluid dynamics, and Bernoulli equations, another energy equations, and applications also we have seen and derived the required expressions in order to solve the fluid flow problems. So, next in the module 3, the boundary layer theory will be the important topic in order to understand the various the flow problems, analyze the various patterns of flows under submerged liquid. So in under a submerged liquid, if a solid body is kept, so how many types of flows will be there, how velocity will be is going to vary, etc. All the parameters can be seen under boundary layer theory. So boundary layer theory is nothing but basically it is whenever a solid body is kept, when the liquid is coming into contact of the solid body, the first layer of the fluid will be going to stick onto the surface of a solid body. So on account of friction or on account of viscosity. So if that is going to be sticked, so then automatically the layer which is coming adjacent to that will be retarded. So but the layer which is sticking onto the surface of a solid body, so then whose velocity becomes zero as it is stationary, the layer velocity is also becomes zero, and if the solid body moves, the layer is also going to move. So but the solid body boundary exactly at the boundary, the velocity will be zero. Gradually it is going to vary from zero to free stream velocity. Actually the mainstream velocity or free stream velocity or the potential velocity is capital U. So initially the velocity is zero. Gradually the retarded all the fluid layers will be decelerated, and the velocity will be gradually increasing from zero to the mainstream velocity over here in a perpendicular direction to the solid body boundary. So but at some point it reaches a free stream velocity. Gradually the velocity is going to vary from 0 to the maximum velocity as which is equals to a free stream velocity. So within this immediate neighborhood of the solid body boundary, the first layer is going to be sticking, another layer will be retarded. Gradually all the layers will be up to some extent, some fluid layers will be going to be extended. Afterwards it reaches the mainstream velocity. So but those who are retarded, such a retarded fluid layers will form a particular region. That region is known as a boundary layer. Within that boundary layer, all the fluid layers will be retarded fluid layers. So on account of viscosity, one layer whenever it is coming into contact of a solid body which is stationary, which is kept onto a fluid, so the remaining layers, the adjacent to that layers will be retarded, and all that retarded fluid layers will be forming a small region, a narrow region. With that narrow region is nothing but a boundary layer. Since the layer of a fluid can't slip away from the boundary surface, it attains the same velocity as that of a boundary. As the boundary of a solid body is stationary, then the velocity of the first layer which is coming into contact of the solid body also attains zero velocity. So in other words, the boundary surface, at the boundary surface there is no relative motion between the fluid and the boundary. The first layer of a fluid and the solid body, between them there is no relative motion. So if there is no relative motion, such condition is known as no slip condition. So as there is no velocity between the first layer which is coming into contact of a solid body and with the solid body boundary and as well as the first layer, both are not the moving respectively with respect to each other. The such condition is known as a no slip condition. If the boundary is moving, the fluid adhering to it will have some same velocity as that of the boundary. So, but if the boundary is having some velocity, it attains the same velocity. If it is stationary, then the fluid, the first layer which is coming into sticking onto the solid body also attains zero velocity as it is stationary. But whenever the solid body is moving, it will attain the same velocity as the body. However, the boundary is stationary. The fluid velocity at the boundary surface will be zero. Thus, at the boundary surface, the layer of fluid undergoes retardation. So, the one layer is, whenever the first layer is sticking to the solid body, the other layers which are adjacent to that stick layer will be retarded. They are also subjected to retardation. So therefore the region, some portion neighborhood to the solid body undergoes a retardation. This retarded layer of fluid further causes a retardation of the adjacent layers, thereby developing a small region in the immediate vicinity of the boundary surface in which the velocity of flowing fluid increases gradually from zero to the mainstream velocity in the direction normal to the solid body. So normal to the solid body, there will be fluid layers, retarded fluid layers, one over other. It will be occupying which is adjacent to the stick layer, which is first the layer will be sticking to the solid body on account of viscosity. So these retarded layers gradually whose velocity is going to be increased from zero to the mainstream velocity. This narrow region of the fluid is known as the boundary layer, the narrow region of the fluid. So from the solid body, if you take from within the neighborhood space, this region is known as boundary layer, where the fluid particles will be retarded. Gradually, all these layers will be forming a boundary layer. The theory which is going to detail about boundary layer and boundary layer characteristics is known as boundary layer theory. In the boundary layer region, since there is a larger variation of velocity in a relatively small distance, there exists a fairly large velocity gradient dv by dy or dou v by dou y normal to the boundary surface. Therefore, the velocity as over a distance is going to vary from 0 to maximum. There will be existence of a velocity gradient. So, in a boundary layer. As such, in this region of boundary layer, even if the fluid has small viscosity, the corresponding shear stress will be equals to tau equals to mu into dou v by dou y is appreciable in magnitude. So in the retarded fluid layers in the boundary layer, so there will be shear stress is acting. The shear stress is equals to mu into dou v by dou y. This is also known as Newton's law of viscosity. So on account of viscosity, only the first layer is sticking, and the adjacent layers also there will be due to the shear stresses. Otherwise, on account of viscosity only, but gradually it varies based on the velocity. So that is equals to the tau equals to mu into dou v by dou y. Farther away from the boundary, this retardation due to the presence of viscosity is negligible, and the velocity there will be equal to that of mainstream velocity. As we have discussed earlier, the velocity is going to vary 0 at the solid body boundary to the free-stream velocity. So if you go farther away from the boundary, the flow may thus be considered to have two regions. There will be two regions. One is close to the boundary zone, in which due to larger velocity gradient, appreciable viscous forces are produced, and hence in this region effect of viscosity is mostly confined. So in another region, outside the boundary layer zone in which viscous forces are negligible, and hence the flow is treated as non-viscous flow or inviscid flow. So in first region, there will be a predominant viscous forces will be considered, that is also referred to viscous flow. But above that flow, there will be gradually viscous forces will be negligible, and it will be called as a non-viscous flow. The concept of a boundary layer was first introduced by L. Prandtl in 1904, and since then it has been applied to several fluid flow problems. So next, when a flat plate, a long, thin, a smooth flat plate is kept under a flowing fluid. So what are the characteristics it is going to be exhibit? So that will be discussed in this topic, especially when you discuss a boundary layer. After understanding the boundary layer concept, what do you mean by boundary layer? How it is going to form? What is the no slip condition? How viscosity will vary, and how many regions will be there over after a solid body, and how the velocity is going to will be going to be existing, how the velocity gradient will be existing. Then if you keep a long thin flat plate under moving of fluid, so what are the various characteristics you can analyze from that scenario will be seen at this point. So say this is a free stream velocity. When your mainstream velocity is considered as capital U, when the stationary object is a long object, a thin narrow plate with a long narrow plate with a smooth surface, if it is kept under a flowing fluid, then it's the the point A at the initial end, at the beginning of this plate, you can be called as this leading edge, and at the at point D, the end of this plate is known as a trailing edge, and these are the two ends, a leading edge and a trailing edge. So up to a certain period, and up to a certain length, from up to B. So initially the fluid will be the first layer which is coming into contact of this plate will be sticking to that on account of viscosity, as we discussed previously while defining the boundary layer theory. So next, the layer which is adjacent to the sticky layer will be retarded. All that retarded fluid layers will be forming the boundary layer, and the boundary layer will vary over by a length of a long plate. So up to this length of a plate, what happens? The fluid particles in this region, in this boundary layer, will exhibit similar to that of laminar pattern. In laminar, how the fluid particles will behave. So how the fluid layers will be arranged. Similar to that, the scenario will the pattern we can be observed in this zone. So therefore, the particular zone from point A to point B in this length, the boundary layer which is to be going to be developed is known as a laminar boundary layer. Whenever it is kept under a flowing stream, the laminar boundary layer will be formed up to this edge only. So after point B, gradually the laminar boundary layer may not be stable. Still, it may not be going to continue after B also. So therefore, it becomes a little turbulent, and there will be turbulent forces. Also, a laminar both these characteristics will be exhibited in this region. Therefore, this region is known as a transition, where the laminar is going to be transformed into turbulent. So there will be some portion which will exhibit similar to laminar, and after that it is going to be converted into turbulent. This region is known as transition zone, that is shown in between B and C. Here this zone is known as a transition boundary layer. So after that, the fluid flow gradually increases, its velocity is going to be increased. It may not be completely laminar or a transition one, but it attains purely the characteristics is similar to the turbulent pattern of flow. So in turbulent, where due to increase in velocity, where the boundary layer thickness is also going to increase rapidly. The boundary layer thickness, a boundary layer, say this much of thickness is there, and in laminar flow, gradually, if you compare with this turbulent flow, this is less in magnitude. So similarly, in transition zone, where it is transforming, the laminar characteristics are transforming into turbulent, there gradually it is increased, but in turbulent, rapidly increase in its boundary layer formation due to this increased in velocity. So over a length of CD, we can call from C to the trailing edge, the particular length is known as the turbulent boundary layer. This is known as turbulent boundary layer. How this velocity and the boundary layer thickness is going to vary. What is the relationship in a turbulent flow will be seen. And in a turbulent, even though it is a turbulent flow, so there will be some portion over the surface of a plate, the just immediate within the immediate portion of that in turbulent zone, very nearer, just adjacent to the that flat plate, it will exhibit similar to the laminar flow pattern characteristics. Therefore, this portion, the small thickness is denoted by delta dash, and it is known as the laminar sublayer. Laminar sublayer is nothing but the some portion of the turbulent boundary layer which is nearer within the immediate vicinity of that flat plate. Some portion of the liquid will be behaving like the laminar flow pattern. Therefore, that portion is known as laminar sublayer. At the leading edge, the thickness of the boundary layer is zero, as it is farther away from the leading edge, then it is going to be gradually increased and it attains the free stream velocity. Hence, a velocity gradient is set up which develops a shear stress. The shear stress will be existing within the boundary layer. Near the leading edge of the plate, the fluid is retarded. Near thin layer, in other words, the boundary layer near the leading edge is relatively thin. As this retarded layer of fluid moves downstream, due to continued action of shear resistance, the more and more the fluid will be retarded. Thus, thickness of the boundary layer delta goes on increasing in downstream direction. So, as it is shown in this figure, it is gradually going to be increased from leading edge to trailing edge. And yeah, the velocity, how it is varying with respect to the boundary layer thickness. So, the relationship and relationship between the boundary layer thickness and the velocity of the fluid will be shown in this diagram. How the relationship is parabolic. In case of these three sections up to laminar, there will be a parabolic. So up to this section, it is a parabolic, but here in this case, in the turbulent zone, it is a logarithmic relationship will be existing. The various factors which influence the thickness of the boundary layer forming along a flat smooth plate are noted down. The boundary layer thickness increases as the distance from the leading edge increases. So the delta gradually increases as it is advancing from the fluid is advancing from a leading edge. The boundary layer thickness decreases with increase in the velocity of flow of the approaching stream of fluid. The greater is the kinematic viscosity, then greater is the boundary layer thickness. So therefore, boundary layer thickness is proportionate to the kinematic viscosity of a fluid. The boundary layer thickness is considerably affected by a pressure gradient dou P by dou x, change in pressure upon the over a distance. In the direction of flow, in this case, a flat placed in a stream uniform velocity of v or capital U, The pressure may also be to assume to be uniform. Dou p by then it can be written as dou p by dou x is equals to 0. So the if the pressure gradient is negative, so in this case we have to assume that that is a converging flow. If it is converging flow, the pressure gradient will be negative. The resulting pressure force acts in the direction of force, and it accelerates the retarded boundary layer. Therefore, the boundary layer thickness will be decreased in a convergent flow, otherwise in a negative pressure gradient. So, if the pressure gradient is positive, then it helps in the thickening of a boundary layer. As the boundary layer develops up to a certain portion of the plate from the leading edge, the flow in the boundary layer exhibits all the characteristics of a laminar flow. This is so irrespective of whether the flow of the incoming stream is whether turbulent or laminar, but up to some portion, it exhibits similar to the laminar flow characteristics. Therefore, this is known as a laminar boundary layer, and it is a laminar boundary zone. If the plate is sufficiently long, then beyond some distance from the leading edge, the laminar boundary layer becomes unstable, and flow in the boundary layer exhibits the characteristics between those of laminar and turbulent. Therefore, that particular zone is known as a transition zone. After the transition zone in the boundary layer becomes turbulent, in this portion of the boundary layer, there is a rapid increase in thickness of boundary layer, and it is known as a turbulent boundary layer. It is this region C2D is known as a turbulent boundary zone. This is turbulent boundary layer. If the plate is very smooth, then some region of the turbulent boundary layer. In this region also, some portion will exhibit similar to the laminar flow. Therefore, that is known as laminar sublayer, denoted by delta dash, and this dotted line indicates the laminar sublayer. The velocity distribution in a laminar boundary layer is parabolic. So that will be represented with this equation capital V minus small v approximately equals to delta minus y square. So there is a parabolic relationship in a laminar boundary layer between the boundary layer thickness delta, and at a distance of y, the velocity is small v, but mainstream velocity is capital U. The mainstream velocity minus the velocity at a distance of the boundary layer existence is small v, and it is approximately equals to boundary layer thickness delta and at a distance of y. And for turbulent boundary layer, it is approximately equals to it follows 1/7 power law. V velocity, the velocity of retarded fluid, is approximately equals to y power 1/7, or it is logarithmic, or it follows v is approximately equals to log of y. So these are the velocity distributions according to the parabolic in this laminar, and up to this section 3 up to transition, it follows a logarithmic a parabolic relationship with respect to the velocity, but in a turbulent it will be logarithmic. For laminar sublayer, the velocity distribution is parabolic, but since the thickness delta is delta dash is usually very small, a linear distribution can be assumed. In laminar sublayer also, the delta dash indicates the laminar sublayer. So this is also assumed to be a parabolic relationship. So in case of laminar zone, it is parabolic, and up to transition also it is parabolic. But in turbulent, there will be laminar sublayer also is existing, even though it is turbulent. So there in that small region also it will be following the logarithmic relationship. The change of boundary layer from laminar to turbulent mainly depends on the velocity of flow v. So of the approaching stream of fluid. The length x is measured along the plate from the leading edge. The mass density denoted by rho of fluid, and it is its dynamic viscosity mu. It is affected by boundary layer. A formation will be affected by these parameters. As such, Reynolds number is equals to rho v x by nu. So the Reynolds number, based on the Reynolds number also we can determine the which zone is laminar and which is transition and which is turbulent. Based on the Reynolds number, it can be distinguished. So Reynolds number is nothing but is a ratio of inertia force to viscous force. It is a significant parameter in indicating the change of boundary layer from laminar to turbulent. The value of Reynolds number at which the boundary layer may change from laminar to turbulent varies from 3 into 10 power 5 to 6 into 10 power 5. In exceptional cases where the approaching flow of free from any disturbance, the values of a critical Reynolds number can reach 10 power 6 or even higher. So based on this Reynolds number, and we can identify which is laminar boundary layer, which is a turbulent boundary layer. And in boundary layer, in the turbulent boundary layer, the Reynolds number can reach 10 power 6 also. However, the change of boundary layer from laminar to turbulent is also affected by several other factors such as the roughness of a plate curvature, pressure gradient, and intensity and scale of turbulence. Based on this, the boundary layer formation and boundary layer thickness will vary. These are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.